Hello, good afternoon everybody. So my name is Jiří Šmídek and I'm from company H-Test, and in my presentation I would like to show you some possibilities of how to measure power consumption of battery devices, and if you measure it better, so you better understand each state of the battery device and you can optimize it in hardware and software better. So resulting this, you can longer your working time of the battery device. So let me introduce our company. It's a small company but international, so we are currently working or operating in 4 countries, and we are serving about 30 people. Our key income is from selling, supporting and integrating Keysight instrument, and if you don't know Keysight, so Keysight is world's biggest company in test and measurement. In history, it comes, we will come to 1939, to garage where Hewlett-Packard started to develop their first audio oscillator. Then during time, the company changed name to Agilent and finally to Keysight. So Keysight has a quite broad portfolio of network analyzers, spectrum analyzers, signal sources, oscilloscope, and other instruments. Let's focus on the topic of my presentation, and it's the low current measurement. So IoT world is almost all battery powered, and users wanted to save life of the battery and producers as well. So there are many techniques how to lower power consumption. So one of it is that the active phase is the shortest one. So there are short transmission and short receiving of information, and at the rest of time the device is sleeping. So but this makes quite difficulties for measurement, because in the sleep mode the device can have only 100 nanoamperes, and in active modes, when transmitting to long range, it can have up to 100 milliamperes. So there's 6 zeros between it, and it's very hard to measure. So if you don't have enough dynamic range, so the signal is what you measure is noisy and less precise. And if you don't have enough bandwidth, so you will miss some short transmissions, so which is for in power very important. There are more solutions how to measure it. So first is multimeter, but it is used for measure the steady state because it's slower measurements. The second is oscilloscope. So if it measures fast transition when the device is active and with higher consumptions. Or there is a special power analyzer which is used to measure as precise as it can be. So let's look for high-end multimeter from Keysight. So this model is 7.5 digit resolution, and the measurement range is from 50 picoampere up to 10 amperes. So if you look at this, so you can say, hey, it's great solution, but there are some troubles with it, and one of it is that if you want to measure very precisely, so you have to take one measurement for longer time. So if you make the measurement longer time, you are missing some states which are fast. Second, it's not measurement in one range. So when the multimeter is doing auto ranging, so it takes some time. Although it is quick, but it takes some time, and again you can miss some details of the signal. In other meanings, when you are auto ranging, it changes internal impedance. So it changes the measurement itself. So to avoid this, you will have to sample as quick as possible to see all important transitions, and you have to set the range to fixed, and then in these conditions you are quite limited in dynamic range, and it's resulting 60 maximum to 75 decibels. So it can be used, but only for steady states where you measure very precisely. For the dynamic transitions, which is quite fast, it can be microseconds long, so you can measure it well with oscilloscope and some current probe. So the probe in the middle, the 1147B, is a current probe that is based on the Hall effect, and even if you will use a high-end oscilloscope with 10-bit sampler resolution and very low front-end noise, the current you can measure lowest is about 1 milliampere. So it's in some devices could be good, but for most of it's not enough. On the market is a special Keysight probe, the N2820, and it has 2 channels. I will explain why. So it's not based on Hall effect. It's based the current measures basically on small precise resistance shunt, and it measures voltage. The voltage is then differentially amplified to see its amplitude. There are 2 channels. So one channel is called zoom in, and you can measure the lowest current possible, so you will see the details of the signal even in the closed sleep mode. And the second channel is zoom out, so you see only the big transition of the current, but the bandwidth is quite large. So for zoom out is 3 megahertz, and for zoom in channel is 500 kilohertz, but still it's still okay. So this is an example of oscilloscope screen when you see 2-channel version of the probe. The yellow one is zoom in, so you see details, and the resolution per division is 2 milliamperes, and the green one channel is zoom out, and there is 20 milliamperes per division. So you can see only big spikes, big peaks of current measurement. But the oscilloscope, if you want to measure power, so what is sourced to your device, is computing both channel, so area under the current waveform computes both probes, and the measurement is called charge, with this amperes per second. Here are conclusion of the measurement with scope and current probe. So the resolution is quite nice at 10-bit if you use our scope. The bandwidth is used for quick transition with higher currents. Sensitivity is from 550 microamperes to 5 amperes, and the dynamic range is pretty good for oscilloscope measurement, and it's due to the 2-channel probe, and it's 85 decibels. Let's look for the best solution on the market currently, and it's a special dedicated SMU. SMU is source and measure unit. So basically it is power supply which has inside multimeter. So the previous solution could only measure, this can only source and measure. So this chassis N6005 is basically can have up to 4 power units, so 4 modules, and it has nice features that it measures simultaneously voltage, current on all modules, on all outputs. It can have integrated oscilloscope function, data logger function for longer measuring, and arbitrary function. So the arbitrary function it's DC, but it can be stepped for some measurements, or it can be modulated as a sine wave. Why is dedicated? So dedicated because it has nice features, and one is simultaneous seamless ranging. So it's not like multimeter. When it auto-scales, it takes some time. The seamless ranging is auto-scaling with zero delay. So, other words, you can measure on all ranges, and in the final decision, you will get the number with just best resolution. With this feature, you can get up to 28 bits of dynamic range, which is equal to 150 decibels. So it's really great function. Next good thing is that you couldn't only source the device and see how it is behaving from power supply, but you can also emulate how it will look like with when it's battery powered. So you can emulate the internal resistance of the battery. So, and here is a graph, so that there is some difference, so that the rise time is not so steep, and the current is a little bit lower. Next feature is that you can measure with this device current and voltage, and don't interfere to the DUT or to the measurement. So the DUT is really powered from battery, and the device is just measuring current and don't influence the measurement, so there is 0 volts at the inputs. At the separate voltage meter, you can measure voltage. With this test, you can do a battery rundown test, so it's a long time measurement, and you are looking at which point is battery is below threshold and the device is turning off. With this test, you can select several batteries with different chemicals inside, which has the best results for the device what you want to test. So there is example of a measurement. So the blue line is voltage, and the yellow is current. And when the current is increasing, the voltage is decreasing. So you can see if there is some pulse, big pulse, which is transmitting some information, that the voltage is decreasing to some maybe dangerous level, which could turn off the device. Let's summarize it. So this solution is very nice. Is a large dynamic range. It has a very fast sample rate. It can sample with 200 kilosamples per second, and the dynamic range is really huge for 150 decibels, and it has some nice advanced features. Let's look for some real measurement. And what else could we measure than module IQRF? So we choose TR7876D with integrated antenna, and the 8 levels of RF power, transmit power. So we were measuring this with the power analyzer, and this is some programmed states of the module. The first 8 pulses is 8 different levels of transmissions. Then there are 3 regions, so it is a different weight implementation. Then there is MCU running and RF idle, so you can measure current. And there is low power receiving mode, so these 2 spikes. And then the white pulse is standard receiver mode. And at the end is sleep mode with watchdog, so it can wake up after some time. So intention of this measurement is not to prove that IQRF are in precise and it reflects to datasheet. But I want to show you that if you are developing your device, you will not use only this IQRF module. So you will integrate some sensors, some maybe another microchip, some keyboard or display, and all this you can measure and analyze each state by state, and you can optimize it with hardware and software. So if you want to make your device operating longer, so you couldn't add more batteries, you could optimize the current consumption. Another picture from RF measurement. So this was taken by spectrum analyzer and from antenna. So this green line is a spectrum at 868 megahertz, and you can see there is a modulation, MSK modulation. The blue line is the 8 pulses which transmit with different power levels. So that's power versus time. The yellow line is IQ diagram. It's in this case it's only line, but it measures how the modulation is good. And the last hope it's visible, the red letters, is the metrics of the modulation. So there is modulation error, off frequency error, or some offset, and the spectrum analyzer can also decode the messages you are transmitting to bits. So so you can decode or catch the record and record what you are transmitting. Now I want to compare it with measurement with current. So with low power mode, you can see that if you increase current, so the transmit level is increasing rapidly. But then the output amplifier is getting saturated. So the increasing current will not increase the radiated power. So it's not worse. It's better to use not the highest power transmission, but the lower power, because the higher power is just a little bit more power, but the modulation is worse because of the saturation of the amplifier. So based on this, you can optimize your states very well, and it's a real example. So these measurement challenges are solved, and the power analyzer is with superior dynamic range over 150 decibels with low noise and precise measurements is very suitable for device evaluation. Thank you for attention. It's all from my side.